I welcome all of you to the tutorial session on the topic 4 on mass conservation. In this tutorial session, I'll discuss 3 example problems. The first problem on filling of a bucket through a water flowing in a pipe. The second problem on discharge from a tank, and the third problem on a piston cylinder arrangement. So the first problem corresponds to a vertically downward flow through a pipe falling in a stationary or moving bucket. So this is a pipe, and the water coming out from the pipe is falling vertically downward on a bucket, which we'll consider 2 cases. Bucket stationary, the first case. The second case, the bucket is moving vertically upward with certain velocity. Now this pipe, the water which is coming from the pipe, there is a nozzle which is connected at the end of the pipe, which is shown separately here. So the pipe diameter is D1, and the inlet, so this portion is connected to the pipe of diameter D1, and in the nozzle the diameter reduces from D1 to D2. Note that the pipe is of constant cross-sectional area, whereas nozzle is a reducing cross-sectional area. So in a constant cross-sectional area, and if you consider the fluid as incompressible, we have a formula which is called as U1A1 is equals to U2A2. So if the cross-sectional area is constant, the average velocity is constant on the pipe of constant cross-sectional area. Whereas in a nozzle, since the area is reducing, the average velocity increases when the fluid flows along the nozzle. This is a pipe, this is a bucket, and the capacity of the bucket is given as 40 liter. And what is given for this problem is the diameter of the pipe is given as 2 centimeter. The diameter of the exit diameter of the nozzle is 0.8 centimeter. So in the nozzle, the diameter of the nozzle is reducing from 2 centimeter to 0.8 centimeter. This curly V corresponds to the volume. I will use 2V. When I'll use capital straight V, I'll call it volumetric flow rate. When I use this curly V, it corresponds to the volume. The volume of bucket is 40 liter, which corresponds to 40 into 10 to the power minus 3 meter cube. And the total filling time of the bucket is given as 50 seconds. And what you have to determine for this problem is the volumetric flow rate. Note the difference between this V, which is shown here, this V, and this V. This V corresponds to volumetric flow rate. This V corresponds to the volume. We have a curly M which corresponds to the mass, and this straight M corresponds to the mass flow rate. For this, in the first part of the problem, we have to calculate the volumetric flow rate and the mass flow rate. And in the second part, we have to calculate the average velocity. As I had mentioned earlier, in a pipe, the average velocity of the fluid is constant because the pipe is of constant cross-sectional area. Whereas in a nozzle, since the cross-sectional area is reducing, so the average velocity increases along the flow direction. And in the third part of this question, you have to calculate the total filling time if the bucket is moving upward with a velocity of 5 meters per second. Note that fluid is entering into the pipe, entering into the bucket vertically downward as shown here. For case A and B, we are considering the bucket to be stationary. In the case C, we will consider bucket moving upward with a velocity of 5 meters per second. So for the case A, for the first part of this question, we have to determine the volumetric flow rate. So one of the very common technique which is used to calculate the volumetric flow rate is to catch the water coming out of the pipe, such as in a bucket here, and take a stopwatch and measure the time required to fill this container up to certain height. So in this case, let us suppose we know the capacity of the bucket, which is 40 liter. So let us allow the water to fill this bucket completely. So we know the total volume which is getting filled up, and we have a stopwatch and we measure the time. So let us suppose we have a stopwatch and the pipe is entering into this bucket, and you find that to fill this 40 liter water, the filling time is 50 seconds. So to calculate the volumetric flow rate, you basically take the volume of the bucket and divide it by the filling time. So 40 liter divided by 50 seconds. So this will give you 40 into 10 to power minus 3 meter cube divided by 50 is equals to 0.8 into 10 to power minus 3 meter cube per second, or it is 0.8 liter per second. Now to calculate the mass flow rate, the relationship between the mass flow rate and the volumetric flow rate is density. Mass flow rate is given as density multiplied by the volumetric flow rate. So when you multiply the density of water, the density of water is 1000 kg per meter cube. So here you have 0.8 into 10 to power minus 3. So when you multiply by 1000, you get 0.8 kg per second as the mass flow rate. Now in the part B of the question, we have to obtain the average velocity through a pipe and at the nozzle exit. So basically, once we know the volumetric flow rate, the average velocity is related to the volumetric flow rate through the cross-sectional area. So if you divide the volumetric flow rate with the area of cross-section of the pipe, which is pi by 1 d1 square. This is the nozzle inlet at which the pipe is connected. So pipe is of diameter d1. So the area of the pipe is pi by 4 d1 square. So divide it, you get an average velocity of the fluid flowing through the pipe as 2.54 meter per second. Okay, so now next we have to obtain the average velocity at nozzle exit as shown here. So at the nozzle exit, you have to divide by the area of the nozzle exit. Now the nozzle exit, the diameter is d2, which is 0.8 centimeter. So if you divide by 0.5 by 4 d2 square, then you get the average velocity at the nozzle exit as 15.9 meter per second. Now here note that if you compare the average velocity at the nozzle exit and in the pipe average velocity corresponds to the average velocity at the nozzle inlet. Okay, so at the nozzle inlet, the velocity is 2.54, which is corresponding to the average velocity of the flow in the pipe. At the nozzle exit, we have a average velocity of 15.9. So you can see that there is around 6 times increase in the average velocity when the fluid passes through the nozzle. So nozzle is a device which is commonly used in pipes to increase the average velocity of the fluid which is coming out from the pipe. Now in the part 3, in part A and B, we have considered the bucket as stationary. In part C, we consider bucket moving upward. So in this case, this problem corresponds to a moving control volume. In this problem, we have to obtain the total filling time. So we will take a control volume inside the bucket, and now since the bucket is moving upward, the control volume is also moving upward. So it's a moving control volume problem. So for a moving control volume problem, whenever we consider mass which is entering, so the mass flow rate entering the control volume or the mass flow rate leaving the control volume, when the control volume is moving, then we have to consider the relative velocity of the fluid which is entering or leaving the control volume. So this is a moving control volume problem. So this is the bucket velocity, 5 meter per second, and this is the vertically downward moving jet which is coming from the pipe, which is at the nozzle exit, 15.9 meter per second. So at the inlet, the fluid which is coming out from the nozzle is 15.9 meter per second. The bucket velocity is 5 meter per second. So as I said, now the relative velocity with which the water is entering into the control volume. Note the note that this is the control volume which we are considering. Now, when this bucket is moving upward, this control volume is moving upward. So there is a relative velocity with which this water is entering, and that relative velocity is given as the inlet velocity, which is 15.9 meter per second, plus bucket velocity, because they are moving in opposite direction. So 15.9 plus 5, that is 20.9 meter per second. This is the relative velocity of the fluid entering into the control volume. Now, when we have to calculate the mass flow rate, we multiply this velocity with the density of the water and the cross-sectional area pi by 4 d2 square. So we use the formula corresponding to the mass conservation, where the rate of change consists of two components: the rate of change of mass stored inside the control volume, which is given here as dmCV by dt. This is equals to the rate, the mass flow rate leaving the control volume. In earlier, I had shown that the rate of change of mass stored inside the control volume plus the net mass flow rate leaving the control volume is equals to 0. Now, when I take the mass flow rate from the left hand side to the right hand side, so on the left hand side, I had mentioned that in a Lagrangian approach, we have only one mass flow. When we have only one rate of change of mass. In an Eulerian system, we have two components. First component, rate of change of mass stored inside the control volume, and the second component is net mass flow rate leaving the control volume. Now the second component, if you take it from the left hand side to the right hand side, which is 0 earlier. So if you take it from the right hand side, then on the right hand side, on the left hand side, it is net mass flow rate leaving the control volume. Or when you take it to the right hand side, it becomes minus. So minus leaving is corresponding to net mass flow rate entering into the control volume. So this is corresponding to m in mass flow rate entering minus mass flow rate leaving. In this problem, there is only mass flow rate entering, there is no mass flow rate leaving, so this is 0. And what we consider, we are here interested in obtaining the filling time. So what we do is that we integrate this dmv, which is shown here, from 0 to mass of the liquid inside the bucket when it is completely filled. So using that, and on the right hand side we have mass flow rate, and mass flow rate is not a function of time, so we take it outside the integrand, and we integrate from 0 to the filling time. So finally we obtain the filling time is equals to the mass of the liquid when it is completely filled, which corresponds to the density of water multiplied by the volume of the bucket, which is 40 liter, divided by the mass flow rate entering. And the mass flow rate entering is density of water multiplied by this relative velocity of water which is entering inside the control volume, multiplied by the area of the at the nozzle exit, which is corresponding to pi by 4 d2 square. So this is the volume of the bucket, 40 liter. This relative velocity is 20.9. This d2 is 0.8 centimeter. So we substitute these values. Finally, you obtain the filling time as 38.1 seconds. Note that when the bucket was stationary, the filling time is 50 seconds. Now, when the bucket is moving towards the pipe, then you find that the filling time has reduced from 50 seconds when stationary to 38.1 seconds. So this is an example problem where the purpose is to demonstrate how do you calculate volumetric flow rate, mass flow rate, average velocity. And this example problem also demonstrate that when you have a moving control volume, how do you implement the relative velocity. In this case, the bucket is moving vertically upward, the fluid is entering vertically downward. So there is an opposite direction. So in the relative velocity, we have taken the summation. If both are in the same direction, then we have to take the difference. Now, this is the second problem. Example problem, this is the corresponding to topic 2. So that's why this example problem is 4.2. This problem corresponds to discharge of water from a tank. So let us take a tank as shown here. This tank, when it is completely filled, this is the height which is shown, which is called as initial height. So the initial condition is the tank is completely filled with water. So the height of the water column inside the tank is hi, and we are interested to know at the bottom of the tank, as shown here, there is an opening from which there is a jet of the fluid which is coming out horizontally. So let me show it to you. We are interested to determine, so our initial condition is that this tank is completely filled up with water till top, and we are interested to know what is the time which is required for half discharge as compared to what is the time which is required for complete discharge. So when we consider the control volume corresponding to the tank, then the height of the tank when it is completely filled up is hi. When it is half filled up, it is h naught, which is hi by 2. When it is completely discharged, this h final will be 0. This is the diameter of the jet which is coming out, and this is the diameter of the tank. This is the diameter of the jet which is coming out when the fluid is discharging from the bottom of the tank. This is the water which is filling the tank. And this is the velocity of the jet which is coming out at the bottom of the tank. What is given to you is the initial height of the water column when the tank is completely filled up, when the discharge has not started, that is 1.2 meter. The diameter of the tank is given as 0.9 meter. The diameter of the jet is given as 1.3 centimeter. This diameter of the jet is 1.3 centimeter, and this velocity of the jet is given to you as under root 2 gh. So note that when the discharge starts, the h is the height of the column of the water inside the tank. So when at time t is equals to 0, this h is equals to hi. When it is half filled up, this h is equals to h naught. So as the height of the water column is reducing as time progresses due to discharge, this jet velocity is also reducing. It is directly proportional to the square root of height of the water column inside the tank. In this case, you have to determine the time when, so our t is equals to 0 corresponds to the tank completely filled up. So we want to know the time at which the tank is half discharge. Half discharge, the initial height is 1.6. So in half discharge, the height will be 0.6 meter. When it is completely discharged, the time is represented here as TF, and in this case the HF is equals to 0. The height of the water column when it is completely discharged will be 0, because our reference height is from the bottom of the tank. Note that actually we should take the height corresponding to the mean location of the jet which is leaving. However, we are assuming that the height of the mean location of the jet leaving is negligible as compared to the total height of the tank. Here I am showing you the fixed control volume or the fixed region that we will be considering, shown by a dotted line. This is called as control volume, and the surface is called as control surface. So by applying mass conservation for a fixed control volume, we have two rate of change. The first rate of change shown on the left hand side here, it is the rate of change of mass stored inside the control volume. In the right hand side, we have the net mass flow rate entering into the control volume. So the rate of So when there is a net mass flow rate entering inside the control volume, then it is expected that the mass of the fluid inside the control volume will increase with respect to time. So considering the control volume with the water level, so in this problem, what we will do is that we'll consider any time instant t at which, let us say, the height of the water column is h. So considering the control volume with water level h at any time instant t, as shown in through this red lines, this is the free surface at that time instant. So at this time instant, if we want to know the mass of the water inside this fixed region or control volume, so this dotted region is the control volume. However, when you have the height of the water column as h, and above this height you have air, and we are just interested into the mass of the water. So when you know the water column has height h and the tank diameter is dt, so the volume of the occupied by the water will be pi by 4 dt square into h, and when you multiply by the density of water, you will get the mass of the water inside this control volume at time t corresponding to the water column of height h. So this is the mass of the water at time instant t, which is equal to density multiplied by the cross sectional area of the tank, which corresponds to pi by 4 dt square multiplied by the height of the water column h. Now at this time instant, you are given that the velocity of the jet is under root 2 gh. So next, first we've obtained this mass of the control volume. The next thing which you have to calculate is the mass flow rate, because we want to calculate this m out. So the mass flow rate, to calculate this is the mass flow rate leaving the control volume. So the mass flow rate is equal to the density multiplied by the velocity, which will be under root 2 gh multiplied by the area of the jet, which will be pi by 4 dj square. So using uj is equals to under root 2 gh, the mass flow rate leaving the control volume is density into velocity into the cross-sectional area of the jet as shown here. So when you substitute this mass of the control volume and this m out into this equation, and you see here that the common term in this two is the density and pi by 4. So this density and pi by 4 from the left hand side and right hand side, it cancels down, and you get dy dt of dt square h as shown here. And on the right hand side, you get this rho pi by 4 cancels down, and you get, there is a negative sign here, so you get negative of under root 2 gh dj square. Now here, note that we have to obtain an expression for time corresponding to half filling, half discharge, and complete discharge. So what we do is that we take integral of dt. So note that in this dt, the diameter of the tank is not varying with respect to time. So you will get on the left hand side dt square dh by dt. So what we do is that we write integral of dt is equals to dt square divided by dj square divided by under 2gh. Okay, so we get as shown here, and we take an integral of that dt is equals to dt square by dj square dh by under root 2gh. Now note that the limit that we are considering is when the discharge is starting at time t is equals to 0, the height of the water column is hi as shown here. This is the height of the water column corresponding to time is equals to 0, and when it is half filled, its height is ho, or which is hi by 2. So from 0 to t0, these are the limit for time. If you integrate it and then solve it, you finally obtain the time for half discharge as 11.6 minutes, and the time taken for the complete discharge is 39.5 minutes. Note that you can get an expression for the complete discharge where in this integral the limit will be hi to 0. Okay, so if you do that, you can obtain the expression for TF. So for the half discharge, it takes 11.6, and for complete discharge, it is 39.5. So if you divide this total discharge time into the time which is required for first half discharge and the time which is required for second half discharge, so then it comes out that for the first half discharge, the time which is required is 11.6. And for the second half discharge, the time which is required is 27.9 minutes. So you can note that for the second half discharge, the time which is required is 27.9, which is much larger as compared to 11.6 minutes, which is required for first half discharge. This is expected because when as the height of the water column gets reduced with respect to time, what you find is as the height of the water column gets reduced, the jet velocity is reducing. So the mass flow rate of the water is which is leaving this tank, which is contributing to the discharge, it is reducing. So the time required for the discharge decreases at later time. Now the second problem, third problem corresponds to oil flow in a piston cylinder arrangement as shown here. So this is a cylinder corresponding to an IC engine, and this is a piston, and this is oil which is inside the cylinder. So this is a cylinder, this is oil, and this is piston. We'll consider a situation where this piston is moving vertically downward, and when the piston moves downward, what you will find is the oil will move upward as shown here. So the piston is moving downward with certain velocity, and this leads to the oil moving upward with a velocity of u0. This is the diameter of the piston denoted by dp. This is the diameter of the cylinder shown here. This is the diameter of the cylinder, diameter of the piston. This is the control volume which we are considering. So this is our control volume. This is the fixed region where we will focus our attention. And the height of the control volume is shown as h. Note that when the piston is moving inside the control volume, the fraction of solid which is inside the control volume will be increasing, and the fraction of the liquid will be reducing. The volume of the control volume is constant, but when piston is entering inside the control volume, more solid is entering inside the control volume, so certain fluid has to leave. So that's why the oil is leaving from the top. So you are given that the diameter of this cylindrical tank is 1 meter. The diameter of the piston is 0.9 meter, and the velocity of the downward velocity of the piston is 0.1 meter per second. And what you have to determine in this case is the oil velocity u0. So you can see as the piston is moving downward, the fraction of solid inside the control volume is increasing and the fraction of the oil is decreasing. Therefore, the mass of the control volume, the mass of oil inside this control volume is not constant during the time when the piston is moving downward. So when we use the mass conservation, we know that in a Lagrangian system, the rate of mass, change of mass is equal to 0. However, for an Eulerian system, there are two rates of change. The rate of change of mass stored inside the control volume, which is shown on the left hand side, and this is the net mass flow rate entering into the control volume. So in this case, there is no mass flow rate entering into the control volume. M in is 0, and you have only M out. So if you consider at this time instant where the fraction of the solid, to show the fraction of the solid, I'm considering the height of the piston. This is the height of the piston. If you know the diameter of the piston, then you can know the volume of the piston inside this control volume at this time instant. So dashed line is showing us the control volume. At this time instant, the volume of the piston inside the control volume will be pi by 4 dp square into h. It's a cylindrical volume, pi by 4 dp square h. Whereas the total volume of the control volume is given by h into pi dc square. So the total volume of the control volume minus this solid piston control volume, if you do, you will obtain the volume of oil occupied at this time instant, and that volume of oil, if you multiply by the density of oil, you will obtain the mass of the oil inside this control volume. So this is the mass of the oil inside the control volume, which is equal to density of the oil multiplied by the this is the difference of the volume. This is the volume of the control volume. This is the volume of the solid inside the control volume. And this difference gives you the volume of oil inside the control volume. So when you multiply by density, you get a mass at this time instant. Now to calculate the mass flow rate, the oil is leaving from this small region, which is the area of this is a cylindrical area, which is given by pi by 4 dc square minus dp square. So if you take the density of oil multiplied by this area multiplied by the velocity, you not note that this is an average velocity of the oil leaving from the top. So if you substitute this mass of the control volume, mass of the oil in the control volume, and this amount from these expressions, and if you take the derivative for the left hand side as shown here, so if you take the time derivative, the cross-sectional area of which is given by pi by 4 dc square is not changing. The height of the control volume is fixed. Okay, so this is also not function of time. So the time derivative will be 0 for this term, and here you will have the cross-sectional area of the piston is not also varying with time, so you will get minus of rho ap dh by dt. Now this dh by dt is what? dh by dt, this is the h at this time instant, h is given as this. dh by dt is basically this piston velocity. So you get AC, AP is given as pi by 4. So as I said, AP will come out, so you'll get minus AP dh by dt. This AP is here written as pi by 4 dp square. This is dh by dt. And on the right hand side also you have the density cancels down from the density you have on the left hand side as well as right hand side, it cancels down. And here you get pi by 4 dc square minus dp square into u naught. And as I said, that dh by dt is up. And note that in this problem, finally we have to determine this u naught. So to determine u naught will be minus dp square into up divided by dc square minus dp square, as shown here. So if you substitute, dp is equals to 0.9 meter and dc is equals to 1 meter, and the piston velocity is 0.1 meter per second. Finally, you obtain the average velocity of the oil leaving upward from the cylinder as 0.426 meter per second. With this, I had come to the end of this video tutorial lecture. Thank you for your attention.